Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine expert. In this tutorial I'm going to show you how to calculate phenological parameter for vegetation cover without any challenge using simple scripting technique in the Google Earth Engine platform and Python API programming. In this tutorial you will learn how to call Nova NDVI product in the Earth Engine platform, how to convert it into the Xarray structure using XEE library, and how to convert it into a data frame, and how to calculate the NDVI for the growing season, and how to find the start, end, and the length of the growing season using the simplest script. So, if you want to learn this tutorial, let's follow this video on my YouTube channel. And remember that this tutorial extendable to all around the world, not limited to only single location, because we are using the public satellite data available for all around the world. Let's make a new notebook in the Colab environment. Let's start with the necessary libraries we need to do programming based on. So, I'm starting with Google Earth Engine related libraries like EE and GEE map. And the next one is pip install the XEE. The XEE is one of the newest library allowing us to combine the Xarray and image collection format. This is very useful and helpful for our analysis in the Google Earth Engine because we can transform the data into the Xarray structure and then apply the existing machine learning packages available on Python. So, and import XE then, and remember to call the Xarray as XR. Let's run the first cell. If you're faced with any challenges or problem in this tutorial, feel free to find the code example below this video in the description box, and you can compare yours with mine, and then easily you can find the issues in your code. And remember to share this tutorial with all remote sensing fans in all around the world. So, once the installation completed, let's clear the output and back to the next cell. Now we need to establish a connection between the Earth Engine and Colab environment. Earth Engine dot authenticate EE library already defined. Then initialize your Earth Engine account. Two arguments are important here. The first is Earth Engine project ID. Go to code editor environment, upper right, and then go to the project info. You will find your project ID. So, for example, my project ID is like this. Copy and paste yours. And the next argument is OPT-URL. If you search about the XEE library, you will find a GitHub page, a detailed instruction about the XEE developers and also the code examples. Here the OPT-URL is actually a unique address that you need to paste or have it in your code before further analysis. It is essential. Now Colab asking permission to access to your Earth Engine account based on a project ID. Select the associated account and then click on continue. As you can see, the connection established, and from now on we can use Earth Engine functions and data catalog in the Colab environment under Python standards. So, in the first step, I need to select the region of the interest, create a new variable called the map function from GEE map. Base map set to satellite view, and then print the map. After a few moments, a user interface appears, and then you can easily define your region of interest using the drawing tools available here. For example, I'm gonna select a vegetation cover, a small area in my own country, Iran. So as you can see, northern Iran covered by dense vegetation cover here. And as you can see here, there are some forest and agricultural areas. I prefer to select the forest here. So you can use the drawing tools available here to actually find or to for the analysis in this tutorial. For example, I will select a point using the marker tool available here. In the next step, we need to have the point as a shapefile in the rest of the code to filter our data based on. So now ROI sets to from map function select the last feature, convert it into a geometry just like this, print the ROI, and then you can see the point shapefile with the correspond coordinates, latitude and longitude. So the next step is calling the satellite data. Go to the code editor environment, and then through the search places and dataset you can find the satellite data. I'm gonna use the Nova NDVI product in this tutorial. The daily NDVI, the daily frequency, is the main important things for the seasonal analysis, for growing season analysis, because we need to have the NDVI for all of the year to find the exact start and the exact end of the growing season based on daily frequency. So Nova NDVI offering the daily NDVI from 1980s, that is one of the valuable products. So let's import, or you can import it, or you can get information through here. So make a collection sets to inside the tuple, just paste the image collection ID. Filter the data based on a period of time you want to study. For example, I prefer to select 2015. Actually, in this tutorial, I'm gonna work on daily NDVI for 1 year in 2015. Dot filter date, and then select the NDVI bands. Go to the bands, and NDVI is available. Select the NDVI band, and there is a scale factor. Remember to make a function and apply the scale factor on each NDVI data through the map loop structure. Make a function lambda sets to, as you can see, img dot multiply the scale factor, paste, and then copy the properties from the input to the output. Properties img.property names to include all existing properties for the new image creating after calculations. Let's run. Make a print. As you can see, 365 element is available. It has the daily frequency. This is the image collection structure, and one NDVI band is available with the properties. Now I can actually transfer the collection from image collection format into Xarray structure. Dataset sets to from XR call the open dataset. Inputs image is a collection, and engine EE CRS sets to EPSG 4326. This is WGS84 ID that is same for all around the world. So, and the scale or the pixel size is very important. If you go to the data characteristic here in the Google Earth engine, you will find 5 km as offered resolution in this satellite data. The scale value here is based on a degree. 1 means actually 100 kilometer, 0.1 10 kilometer, 0.01 like this is 1 kilometer. So, but here we need to have the 5 kilometer, just like this. And the region of interest, geometry, sets to the ROI. Now the image collection transformed into the Xarray structure for only that point, the region of interest. Let's run the dataset. Here we have a multi-dimensional structure that you can see the NDVI value only for this latitude and longitude, and the temporal information is also available here. There it is. In the next step, I need to convert this Xarray structure into a data frame, because in that case it is easier to handle the data with the data frame. So as you know, we have only one single value for the selected point per date. So that's why a data frame structure could be really useful and easier to process in the next step. So the data sets converted into a data frame using two data frames, just like this. The latitude and longitude is same for all the dates, but we need to get rid of them. So to do this, we need to actually reset the index to able to select the NDVI and time. So first, remove the existing index just like this, and then select the NDVI or time and NDVI. Time and NDVI. So as you can see, only two columns, time and NDVI, remained. So it is important to set the time as index in the further analysis. So now to index or set index time, and here the previous columns, the extra column or column number now deleted, and only time as index and NDVI values remained. So it is possible maybe we have some no data values in the time series, and it causes some uncertainties in the further analysis. You can fill the no data values by interpolation technique. Interpolate based on linear regression. So the method sets to linear, yes, and let's run. These are the same values, but for those dates we had no values, it will be filled using the linear regression. So now make a variable for this script. Let's run. Okay, the data frame is ready to use. So let's make a plot to see the NDVI variation in this region. As you can see, the NDVI actually highly variable because of the cloud cover, noises, and etc. So here I want to show you how to manage these errors and uncertainties and high drops and high jump values in the time series. So one of the filters typically used in this case is Savitzky-Golay filter. So hopefully it is available in the SciPy, and now easily we can call and apply on NDVI data. So from SciPy dot, for example, signal import Savitzky-Golay filter, just like that. So now let's make a new column in the data frame. This is a smooth NDVI. So there it is. The smooth NDVI sets to bring goal filter first, and now at the arguments, the first NDVI values defined. The next is window length. The window length is very important. The higher window length, more smoothness, and vice versa. So, and I prefer to select, for example, 30 because I need to actually have, I want to actually see the 30 days NDVI dynamics, because when you are applying such kind of filters, some of the NDVI current NDVI values converted and or smoothed. In this case, you will set a window length to define how much detail you want to have in the output. Although the temporal frequency will be remained as a daily, but here each day value is actually affected by 30 days analysis. So, and the next parameter is poly order. For example, you can set it 2 or 3. It's totally up to you. Let's run and easily apply it. Now a new column added. This is smooth NDVI. You can select the NDVI smooth and make a plot based on. There it is. This is actually before smoothness, and this is the after smoothness. Savitzky-Golay is one of those filters specifically offered for the NDVI phenological analysis. If you search on the net about the NDVI and Savitzky-Golay filter, you will find a lot of literature addressing this method for phenological analysis. So, for example, if I actually reduce the window length to the 10, then you will have more details or more detail of variations in the NDVI. It is up to you what kind of variations and dynamics detectable in the final output. Or you can increase the poly order here just like this to see how much it will have impact on the quality of the output at the end. So experimentally, I prefer to use the poly order 2 and 30 days here, but case by case it's different, and also your aim of study will define how to set these parameters regarding to the situation you will have in the region of interest. Okay. You can see the NDVI ranging from 0.1 to 0.6 based on the modifications and smoothing process. Now I need to set a threshold and find the start and end of growing season based on. So make a new cell and then a new variable as the threshold. So, for example, from a visual interpretation, I will get that, for example, the growing season could be a start from, for example, some values between 0.3 and 0.4. For example, 0.3, 0.35 considered as a threshold in this study according to what I interpret from the NDVI dynamics in this region, because as you know, higher NDVI, higher chlorophyll content and higher density, returning higher, reflecting higher density and higher chlorophyll content. So in this case, I guess that 0.35 could be a good threshold for my region of interest. And also there are some statistical method to find the threshold, then you can find them and apply, and let's see how it works for your region of interest. But I prefer to use some single values I can get from a visual interpretation from NDVI dynamics in my region of interest. Okay, this is the threshold, and I have the NDVI smooth value or reconstructed value for the growing season. Just like this, you can see here. In the first step, I need to find those NDVI those smooth NDVI values, NDVI smooth, that are greater than, I'm making a query, that are greater than the threshold. So for example, my threshold is 0.35, and here you can see all these NDVI values with the dates and the values, all of them actually here listed and available for the for our year. So now if you get the index value only, you can see that actually the start and growing season dates, start and end, is available here. The first date, or the first time in which NDVI, for example, grows above or raise above zero point 0.3 is, for example, June 10 in 2015. So if I select the first item, so index 0, you can see the start of growing season selected. It is really easy, and you can get the date information only using this. So this is a start of growing season. You can see it is really easy and without any challenge. So let's make a print, and a start of growing season. So SOS, this is sets to the SOS. So something's wrong here. Yes, we should write it like this. The parentheses removed. Now we have it here, SOS, just like this. So now we can pick the last. As you can see, we back to the threshold values, and again we want to have the indices or index values. The last index refers the last day in which NDVI value was above 0 0.3. We can consider it as the last day of growing season, for example. So how to select it? Index -1. So there it is. The last day selected, converted into the date, just like this. And this should be end of growing season, EOS. Let's make a print. This time, end of growing season, EOS. There it is. The end of growing season calculated. So, and now when you have the start and end of growing season, you can easily find the length of the growing season. So how to do it? Again, so now there is a simple equation. The differences between end of growing season and a start of growing season. Start of growing season. Put them in the tuple, just like this. You can see we have 90 days, so we want to get the days without the rest of the things. So select the days. So but in such equation as it is suggested by Python standard, the values one value actually missing in this calculation. That's why you need to add it to 1, or add a +1 at the end to actually fulfill the missing 1 day in this equation. So now here it is, the length of the growing season. Print f length of growing season, LOS. There it is, 91 days. This is actually the length of the growing season, and the code is ready, and you can see how it was easy to calculate for your region of interest. Now you can easily change the date, for example, to another year, 2016 to 2017. Let's run the same cell without any challenge and without any update in the code. You will see the new result, but this time for another year. So you can see that somehow NDVI changing based on the situation. So for another year, for example, you can see the different values for start and end of growing season, and also you can easily see the length of the growing season. I hope you like this tutorial, and I hope you can get enough information about the growing season phenological analysis. If you had further question or comment, feel free to share them in the comment part below this video on my YouTube channel. Thank you for your attention.